In this video, we're going to talk about how to assess whether the errors of a regression model appear to come from a normal or Gaussian distribution. And there's various ways that you can check this assumption. We're going to focus on one main approach with one testing approach that I'm actually not a huge fan of. But the main approach that I like to use for checking whether the error assumption, the normal error assumption, is satisfied for regression models is using something known as a QQ plot, where QQ stands for quantile-quantile. And a QQ plot, what it does is it compares the residuals from our fitted model to ideal observations coming typically from a normal distribution. And so it takes the residuals and sorts them, and then it compares them to a plot of quantiles from a standard normal distribution. And this is the mechanism that R typically uses for constructing these QQ plots, though there are slight variations for other distributions such as the T distribution. The big picture, so here's the big picture, we don't want to get lost in the details. The big picture for these QQ plots is that if the errors are normally distributed, that means that the residuals should also be normally distributed. And so when we look at a QQ plot of our residuals and we compare them to a normal distribution, then what we observe should match what we expect, and the points of our QQ plot should lie approximately in a straight line at a 45-degree angle. So essentially there should be a one-to-one relationship between our observed residuals and the quantiles that we expect to see from a normal distribution. And so here are some examples of QQ plots for different types of data. So what I did was I generated data from different distributions and I constructed a QQ plot under the normal assumption for those data sets. And so in this first plot, in the upper left panel, we see a QQ plot for data that actually does come from a normal distribution. And we see that these points don't fall perfectly into a straight line, but for the most part they follow that 45-degree reference line. There's a little bit of deviation, and they're within those 95% confidence bands that the function will automatically produce for you. It's frequently that instead of having normal data, we might have positively skewed data. So we might have data that looks something like that in terms of a histogram or a density function. And if we have positively skewed data, you can see that the points they really depart quite a bit from that straight 45-degree line, and they pretty quickly start deviating from the confidence bands. And so essentially the pattern we expect to see if we have positively skewed data is this curve here. So it starts low and then it angles upward, and that would be a situation where we had positively skewed data. If we had negatively skewed data, by the way, it would actually flip like on a mirror and look something like that. So in either case, whether it's positively skewed or negatively skewed, we have this strong sort of parabolic curve, flat parabolic curve that will show up in our QQ plot. On the other hand, it sometimes happens that we observe data with heavy-tailed errors. So heavy-tailed errors, or heavy-tailed data, essentially means that the probability of extreme events is more likely than what you would expect from a normal distribution. So if this were, for example, a standard normal distribution, a heavy-tailed distribution might have heavier tails, where the probability of these extreme events is greater than for the normal distribution. And it's a little bit difficult to tell from just this one plot, but with these heavy-tailed distributions, you expect to essentially see something like this. And because we can get these really extreme observations, it doesn't always look exactly like that, but that's the overall pattern we expect to see if we have heavy-tailed data as opposed to normal or Gaussian data. Sometimes instead we observe light-tailed data, or data coming from a light-tailed distribution. And a light-tailed distribution essentially means that we don't have extreme events with as much frequency as a normal distribution. So in this example, I actually just generated data from a uniform 0-1 distribution. So we're never going to get extreme observations in the tail. And light-tailed data actually often is pretty compatible with Gaussian data. You often can't obviously tell the differences, but if I plotted enough of these, you would sort of see a pattern where it's kind of like this stretched out S, and this would be an indication that we have light-tailed data instead of Gaussian data. In this case, the violation from the normal assumption was not so great that we saw a ton of deviation, or a bunch of points outside the confidence bands. But we do see a few out here in the edge of our QQ plot. So those are 4 examples of QQ plots for different kinds of data. And you may be asking yourself, well, why not just use something like a histogram or a box plot? I've learned about those before, I understand those, so why not just use those to assess normality? And you can do that, but those are really not very good graphics for assessing the normality assumption. So box plots in particular are really bad in my opinion because they really only provide something like 5 pieces of information. They show you the minimum, the maximum, the 25th percentile, the 75th percentile, and the median. And depending on the way that you plot them, they sometimes show specific outliers that you may have in your data set, but you throw away a lot of information. You basically compress all the information down to 5 different numbers. So box plots are not a great way of assessing normality. Histograms, on the other hand, are a little bit better, but the shape of your histogram can strongly depend on the number of bins that you use, number of vertical bars you use when constructing that graphic. And so it's not an ideal tool for assessing normality of your errors. And so I really like the QQ plot because QQ plots are designed to look at or provide a detailed description of a data set's distribution. And so I really think that you should stick with QQ plots in R since they are so easy to construct and they give you so much information. So if you really don't want to use a QQ plot or you really don't like interpreting a QQ plot, there are actually many tests of normality that you can do. I'm just going to mention one. It's not by any means the best, but it's pretty well known. It's called the Shapiro-Wilk test. And the null hypothesis in our context would be that our residuals are a random sample from a normal distribution, which they would be a sample from a normal distribution if in fact the errors are normal. The alternative hypothesis is that the residuals are not a sample from a normal distribution. And one of the things that you have to be careful of is that we're assuming we have a random sample when we're doing this test. And that's frequently not the case when we're building regression models. You don't have a random sample of data. And so just on the surface, I am very skeptical that the assumptions of the Shapiro-Wilk test will be satisfied before we actually do the test. And so I think it's not a great tool for assessing normality in my opinion. I actually don't think any test is a great tool for assessing normality. However, if you did want to use this approach, then you can use R to perform this test pretty easily. It will provide a p-value from which you can make your decision. And while the Shapiro-Wilk is a tidy way to assess normality, it gives you a clear-cut yes or no answer for the most part, it's not nearly as flexible as a QQ plot. So it doesn't, for example, suggest a way to correct the problem. So a Shapiro-Wilk test might say, yeah, there is a problem with the normality assumption, but it doesn't tell you, do we have light tail data, do we have heavy tail data, do we have skewed data? So I really feel like the QQ plot gives you more information about how you might handle a violation of normality when you're looking at the QQ plot of your residuals. Additionally, the Shapiro-Wilk test can be easily influenced by 1 or 2 points that deviate from normality for large data sets. And as we'll see here, really, as long as you have enough data, the central limit theorem is going to kick in, and this normality assumption is not terribly important for most things that we're going to do. So even when the errors are non-normal, our estimates can still be unbiased, assuming that our model is correct and the error mean is still 0. Your tests and confidence intervals are not going to be exact, but the central limit theorem actually applies to regression models because our estimated coefficients are essentially a weighted average of the data. And so as long as we have a large enough data set, then our test our hypothesis test and confidence intervals will be approximately valid, and their accuracy will increase as we increase the sample size of our data set. If you have short-tailed data, or you have short-tailed errors, then the consequences of violating the normality assumption are pretty mild. You can essentially ignore that. If that assumption is violated with short-tailed errors, then there's really no practical impact on the validity of our confidence intervals and hypothesis tests. If you have skewed data, then frequently a transformation of the response variable will correct the problem. Heavy-tailed errors are a problem. So if you have heavy-tailed errors, then you don't really want to trust the inference made with hypothesis testing or the confidence interval you get, because those large values, those unusual errors, can really impact your analysis. And so if you know that you have heavy-tailed errors, it's probably a good idea to use some sort of robust regression method instead of just using ordinary least squares regression to fit your model. So how do we actually go about assessing normality? So I've talked about the QQ plots, but what functionality is there within R to check these assumptions? So the function that I like to use the most is the QQ plot. Notice it's a capital P function in the car package. So once again, you have to load the car package before you use this function. But if you use the QQ plot function in the car package and give it your fitted linear model LMOD, it's going to produce a QQ plot of our studentized residuals. So see one of the previous videos where I discussed those. And under certain assumptions, we know that the studentized residuals have a t distribution. And so this function will produce a QQ plot of the studentized residuals along with t-based confidence bands, 95% confidence bands for the residuals, giving us an idea of what we expect to see if in fact the errors are normally distributed, mean zero, and constant variance sigma squared, and are uncorrelated. So that's the function I like to use the most to assess normality. It's just the easiest one to use. It gives us a lot of information. If you don't want the confidence bands, you actually can use the plot function on your linear model and specify which equals 2. And that will produce a QQ plot of your standardized residuals, which are fairly similar to the studentized residuals, but use a different estimate of your error variance. And that function will create the QQ plot along with your helpful reference line. Lastly, if you want to do a Shapiro-Wilk test on your residuals, you can use the residuals function on your LMOD to extract the residuals, pass those to the Shapiro-Wilk test, and R will perform that test for you automatically. So let's look at our savings example once again. So here we see a QQ plot of the studentized residual of that savings data for the 50 different countries. And we have the confidence bands, which is a really nice reference to give an idea of whether this assumption is satisfied. And outside of maybe this one point over here, all the points appear to be within our confidence bands. And one thing I should mention is that having a single point outside these confidence bands is not necessarily a death sentence. We have 50 observations here, and if we have a 95% confidence bands, we would expect that something like 1 in 20 of the points would randomly fall outside those confidence bands by random chance, even if the assumptions were perfectly satisfied. So seeing a single point outside the confidence bands is not worrying, especially when there's no clear systematic pattern. If we had seen our points, for example, going up here or something like that, that would be an indication of a problem. But just seeing one point down here fall outside those confidence bands is not an indication that the normal error assumption is violated. I would caution you, so if you start seeing 1 or 2 points out here that are outside the confidence bands, that would be a little bit worrying to me because that might be an indication of some sort of systematic pattern that you would see if you had more residuals. So it's not a guarantee that the error assumption is violated, that the normal error assumption is violated, but I would definitely be more cautious in saying that the residuals are compatible with the normal distribution when I start seeing residuals at the endpoint of my QQ plot falling outside those confidence bands. I mentioned that you could get a slightly less informative QQ plot using the regular old plot function. So here that is. So it does have the nice 45-degree reference line still, which is helpful. And we see our points are pretty closely following that. But the reason I prefer the former plot as opposed to this one is that the previous one had those confidence bands, and it gives me a better idea of exactly how much variation I can expect to see within my residuals in our QQ plot. So lastly, I did perform a Shapiro-Wilk test on the residuals of our fitted model. This test statistic right here, we didn't even look at the form of the test statistic, so we can't really quantify whether that's large or small. However, when I look at this p-value of 0.85, that is a very large p-value. And so I'm going to fail to reject the null hypothesis that the residuals are a random sample from a normal distribution. Granted, there's still the issue of whether in fact the residuals are a random sample at all, but at least the residuals are consistent with a random sample coming from a normal distribution. So we have insufficient evidence to conclude the residuals come from a non-normal distribution. In case you were interested in the actual code I used to produce some of the plots in this video, I'll just briefly explain some of them. So the first plot that we saw was a plot of 4 QQ plots. There are 4 different panels, one for normal data, one for right skewed data, positively skewed data, another for heavy tailed data, and another for light tailed data. And so you can see here what I did was I created a graphics device with a 2x2 plotting grid. I set my random number seed so that I could get reproducible results. And then I constructed a QQ plot for 50 observations randomly sampled from a normal distribution, 50 observations sampled from a log normal distribution, which is an example of a positively skewed distribution, 50 observations randomly sampled from a Cauchy distribution, which is a heavy-tailed distribution, and 50 observations randomly sampled from a uniform 0-1 distribution, which is an example of a light-tailed distribution. And then I reset my graphics device to a 1x1 plotting grid. So that's how I created the set of 2x2 set of plots, looking at how the QQ plot deviated or changed for different types of data. And then I have the 3 other functions I use to produce the other results we saw for the savings data that we've already interpreted.